Hi, so I just wanted to finish the last part of this problem because we ran out of time. So, with that said, here we go. We're still solving for acceleration, so I'm going to do that. So I get m2 over g, m2 times g over the sum of the two equals a. Notice that there are no numbers in this problem, that this would be the answer. So there's a value to learning, even though I was doing it in the last couple problems, a value to learning how to solve this algebraically like that. So the key to this problem was recognizing that the acceleration is going to be along this way. And the acceleration doesn't happen in the y direction, it only happens in the x. Which is why we kind of just, I'll even put little x's here, worried about this. But once it goes over the side, it becomes completely a y. And just to go over, lastly, our direction for positive we said was down because it's going down like this, and the direction for positive is like that. So that's the reason why you solve it like this. Some other things just to point out too, this is a thin chord, which means the chord has no mass. Smooth surface means there's no friction. And then it does this. So let's quickly just do it with friction just for the sake of argument. So let's say we have the same setup with the pulley. We have the object hanging, M2, M1, but now let's say we have friction. How does this look now? So we get the same FBD for the first one where we have gravity, but the surface cancels it out, so we don't have any acceleration along this direction. We'll have tension, but then we'll have friction, like that. So let's assume once again that the acceleration is in this general direction for positive. So tension minus friction equals MA, M1A, like that. So we can rewrite this as force normal times mu equals M1A. Now remember, that's because force friction is equal to force normal times mu. Now since we're at a horizontal surface, that means this will actually be T minus mg for force normal, so these are equal, times mu M1A. So it basically, as you can see, it just adds an extra term right here. So it's not too much more. And then same thing, this becomes FG2, so this one was 1. Remember that. And then we have tension. So this remains the same. Like that. We can use the same method of adding equations, so let's do that. So then let's add this one, M2G. So I just switch this to M2, because remember FG is equal to MG minus T. I don't know why I put a 1 there. There's no reason for that. There we go. M2A. T's go away. We get M2G minus M1G mu equals M2A. So as you can see, we can kind of now write an expression. Let's go down a little more. For the acceleration, g's can come out, but nothing else. So g comes out. M2 minus M1 mu equals M2A, where A is going to equal to all of that divided by M2 equals A. So if we compare with friction, here's without friction. Oh, sorry. Almost. Big mistake was I forgot to add in this piece here. Alright, let's fix that. Almost there. And you might have caught that, so I thought that looked a little funny. There we go, sorry about that. Let's fix this. So remember we had to add these two. Let me do that. That would be more clear. So those have to add up. There we go. Alright, so the A's come out, so I get this. There we go. Perfect. Now it's showing what I wanted to say and talk about M2 minus M1U over the sum of them equals A. Perfect. That's much better. Now if we compare, you can see that we have M2, the full value, over the sum of the two. But when you have friction, you can see that sum of M2 is taken away by friction. So as you might imagine, it's a slower acceleration, which is perfect. That's exactly what we wanted. So anyway, that's the end of this systems segment of our Newton's applications.